All right, D, how we doing this evening? It's Friday night, about 8:05. I figured I'd get my second video done of the day. First video I did today was for home mechanics. We did how to get your lawnmower ready for spring. So now I'm going to work with you guys on getting 4.1.2. I got 4.1.1 done for Fish. He got the part done for the most part. Nice job, Fish. I really enjoyed talking to you guys yesterday. It was nice catching up. So here is 4.1.2. So state machine design using the S7. So here's what we're going to get into. So let's get into it. So a synchronous sequential circuit consisting of sequential logic section and combinational logic sections, outputs, and internal flip-flops progress through a predictable sequence of states. So input, flip-flops, outputs with a clock. So input, combinational logic, memory, and output. These are the three parts of a state machine. So what should happen next based on button switches and other inputs? So that's our combinational or our input logic. And then flip-flops determine the number of states of the design or the trigger of the states or transition based on the inputs. So how many different things is it going to do whenever you push that button? And then the output is what motors, indicators, or the output should do once the flip-flops have caused the transition to a new state. So some everyday devices that use these. Traffic lights. There's three states. Fish, this is going to help you if you continue to work on your design for your showcase project. Whether we have showcase or not, that's still up in the air, but I hope that this helps you a little bit with your showcase project. Garage door numeric keypads, vending machines. These are all different types of state machines. So we need to create a state graph, determine the number of states and label it, and then determine the number of state variables, label how many flip-flops we need, outputs, and encode outputs to states. Create transition tables from graphs, write and simplify the transition table, and then design the circuit. So this is a state graph. Shows the sequence of the states that the state machine will transition to on each clock transition. So state 0, state 1, state 2, state 3. And then, so there's 4 states in this one. And this is the Milo Tollbooth Company's switch. And it shows open switch, open limit, close limit, motor open, motor close, gate open, gate closed. So we have a whole bunch of these different options here in our state graph. So then each state graph contains a bubble. It's labeled state 0, 1, 2, and 3. These are labeled arbitrarily. Try to go in sequential order. Each transition arc is labeled with values of the input variables that make the transition occur. So here's our input variables. OSX, OSX, that looks like a C or OL, 0, CLX. So that must be a C. It's hard to see right here. So here's our input loop. So 0, 0 gives us that, 0, 1, 1, 0, and 1, 1. Remember, everything's always a truth table. So outputs, again, 0, 0, 0, 1, 1, 0, and 1, 1. So we have our transition arc up here. For input, x equals 0 is hold state. Input variable is x. The state is state 0. The variables are QA and QB, 0, 0. Output variables, y equals 0, z equals 1. And then our transition arc to our next state or next state bubble, x equals 1. So if this is a 0, we're here. If it's a 1, we go here. State variables are actually the outputs for the memory flip-flops. So QA, QB, here's our memory of our flip-flop. So Q1, Q1. So the 4 state examples would require 2 flip-flops, QA, QB. The clock passes through 4 states. So each flip-flop is 1. So QA is on one flip-flop, QB is on a second flip-flop. That's how you get 0, 0, 0, 1, 1, 0, and 1, 1. If the 5th state was needed, how many flip-flops would we need? It is not possible to have exactly 5 states. How many states would go unused then? So if you said 3, and if you said how many? You can figure this out. Each state bubble is assigned an output variable then. This example has 4 output variables based in what state it is in. So if we look down here, we have motor open, motor closed, gate open, or gate closed. So is the motor moving? Yes or no? Is the gate open or closed? Yes or no? And then here's our transition. So present state, state 0, which has a 0, 0, always. State 1 has a 0, 1, always. State 2 has a 1, 0, always. State 3 has a 1, 1. And then we have our do not matter conditions, our highs and our lows based on each one of those. How do we get to the next state? So we go from here to here, and then we go from here back to S0. So it tells us exactly how we're going to transition through this. Then we can use Boolean algebra and figure out our wonderful design equations to get through there. Notice that each state occupies 2 lines on the transition table. That is because in this, the transition is triggered by only one of the 4 possible inputs at any time. So causes transition, S0, if it is 0 and 1, it transitions. 0 and 1 transitions. 0 and 1 transition. 0, 1 transition. So this is what causes our transition to the next state. So in the state machine, the next state is actually the output from the memory flip-flop, QA, QB, when the input is changed. So QA, DA for the next state on one flip-flop and DB for the next state on the other flip-flop. So the outputs from memory flip-flops are linked to the input combinational logic. That way the transition is made on the next clock signal to the next state. So here's where we have our memory outputs, flips to our input logic. That way we get that flip to the next state. If this isn't here, there's no movement to the next state based on the clock hitting here. So then we have our input combinational logic. DA equals Q, DB equals DQ. Examples of 4 outputs: motor open, motor closed, gate open, gate closed. And then this tells us what has to happen for those to occur. Design a state machine that will count out the last 4 digits of a phone number only when the enable push button is pressed. The output should hold the last number until the enable button is pressed again. So you're only making 4 and you're going to do your phone number. So whenever the enable logic 1, the output will continuously cycle through the 4 values, 4, 6, 9, 1 in this example. Whenever the enable logic is 0, the outputs will hold at the current value. So it only transitions on the button push. It doesn't transition unless I do something. So state 0 is a 4, state 1 is a 6, 9, 1. Enabled, it holds at 0. Go on a 1, it goes to the next one. Holds at 0. On a 1, transitions to the next state. Holds at 0. On a 1, transitions to the next state, and so on and so forth. And it will continue in this loop forever. And then we need to determine a number of state variables and assign them. So 0, 0, 0, 1, 1, 0, 1, 1. There's our 4 state variables. So then 0, 1, 0, 0. Now why are there 4 here? Excuse me. So we have our inputs. 0, 0, 0, 1, 1, 0, 1, 0, 1, 1. Enables, flips to the next state. State 0, state 1, 1, 2, 2, 3, 3, 0. What is our next state here? What are inputs to get there? And what outputs do we want to have? So then write and simplify our design equations. So if we look, we have not QA, QB, EN. And then we design our AOI circuit. So all you're doing is plugging in your equations. Here's our switch. QA, QB. Make sure you use probe so you know whenever it trips that it's going to be right. We have our two flip-flops. And then the question is there a better way to enable this logic here? So we can go to eliminating some gates, even though it's PLD and it really doesn't matter. We can use exclusive OR in this particular case, because then it would have to be one or the other. It can't be both, which is basically what it said back here. So we have and there's no option for it to be either one, so it has to be an exclusive OR. So then we have our input logic, our memory, flip-flops, and then our output. So here's our input logic, our memory flip-flops. Notice there are two 5-volt power supplies to these. And then we have our output logic to output what we want. Be a 9421 in this case. So there's our inputs. All I do is flip the switch back and forth. Here's our input logic. There's our memory flip-flops, and here's our output logic. Or I'm sorry, our clock. Forgot about the clock. And then our output logic is over here. So that is a state machine in its simplest form that I can come up with for you guys. That is your next assignment. I'm going to tag it with this video. All right, guys, have a great night and be great.